Okay, this is going to be our second video in our electric potential series, and so we'll get right into it here. Well, everything that I'm going to be talking about here corresponds to section 23.2 from the text, and we're going to be talking about electric potential specifically right now. So in the last section, we looked at electric potential energy. So we're looking at the electric potential energy of a test charge, so Q naught in an electric field. And we now want to be able to describe this potential energy on a per unit charge basis. So very similar to the way that in earlier chapters we had a force due to the electric force, right? So we had some force, as we see here, and we wanted to be able to describe this force on a per unit charge basis. Well, we simply defined the electric field in this way, and I mean I could have written this maybe a different way. We kind of ended up setting it up like this, right? And so we took our force, divided out the charge, and we were able to define this electric field that allowed us to talk about the force per unit charge, right? And so that's kind of the similar idea of what we're going to try now, but in this case we're going to be looking at electric potential energy on a per unit charge basis. Okay. So the potential, written here, which we give the symbol V, or sometimes called the electric potential, is our potential per unit charge, and it can be written as the equation that we see here. Maybe I'll leave this in for the notes. Okay. And so the SI units for this potential are going to be volts. Okay, and 1 volt is just 1 joule per coulomb. Okay, so those are the SI units that we're going to work with. Let me scroll down a little bit here. So we're going to start by revisiting the expression that we had for work as a change in potential energy. This is the stuff we would have talked about in Physics 111, but we also reviewed last video, right? And so what we saw last video was basically we basically saw this expression, but with none of these Q's dividing stuff out, right? So just the upstairs portion of all this, right? But now we're going to go through and we're going to divide out the charge, and again this is because we want everything on a per unit charge basis. So if we go through and we divide the work by our test charge, by the magnitude of our test charge, and we do the same to the negative of the change in potential energy, and we expand that out, and then we apply, well, once we're at this stage, we can apply the definition that we just built up for our potential, and we see that we can define our work over our charge in terms of this change in our potential, right? So if we do that and we just go through and rearrange these minus signs, this final equivalency here, this is just a different way of writing things. So basically what we have here is VA and VB. These are our potentials at points A and B, where our potential is this new quantity that we've defined up here. Okay, and the difference, VA minus VB, which is sometimes abbreviated as we see here, and the subscripts really do matter here. You really want to make sure that you have VA minus VB. So VAB is VA minus VB, where VBA would be the opposite, right? So be careful with the subscripts. But so this is called our potential of A with respect to B, or more commonly called, I'll probably more often call it the potential difference between A and B. Okay, and so I'm not sure if you guys will have already seen this in your labs or not, but we're going to take a look at these in the lectures, or at least do some calculations with these in the lectures, and you might have seen them in your labs already, and if not, you will see them soon. Voltmeters are what measure this potential difference when we're actually doing stuff in the lab. And as I said, you guys will see these soon if you haven't seen them yet. Okay, so we're going to be interested in calculating electric potential or potential. And so in the last section we saw that our potential can be written as we see here, right? Or I should say, I should be careful. Our potential energy can be written as we see here. And we can simply define the electric potential or our potential V by dividing out the test charge. Okay, so we have our definition here. This is the definition that we're going to use for our potential. And if we wanted to find the potential of a large collection of point charges, just as we've done it several times now, we can sort of invoke this principle of superposition. We can just add up all the contributions of each point charge to our potential, and if we add them all up, we're going to end up finding the potential due to the whole charge distribution that we're looking at, and that's the expression that we see here. This is very similar to what we would have talked about last video with potential energy, right? And then finally, if we have a continuous charge distribution, so we have some sort of a macroscopic object that we're then going to break up into tiny little chunks of charge, we can see that we can do this. We can divide our object into tiny elements of charge dq, and then we end up getting this integral like we have many times before, where we need to do an integral over a bunch of little pieces of charge, right? And that's how we would find the potential due to some sort of a macroscopic object, right? So before I move on here, let's just explore the question one more time. What is electric potential? Electric potential is the electric potential at a certain point is the potential energy per unit charge at that point. So we want to be thinking about potential energy per unit charge at that point is given to us by our potential. Okay, so V at a certain point gives us the potential energy that a charge would feel at that point. Okay, and so one way to calculate the potential is to use this sort of relationship that it has with the electric field. If we know the electric field, we can get to our potential at that point, and that's what this little next section here sort of discusses. So what we're saying here is that if the electric field is known, we can find V from E by looking at the following expression. So this should be familiar to us. This is our expression for work in terms of an integral F dot dl. So we're dotting our force into the tiny chunks of displacement, right? And we can rewrite the force because we're dealing with an electric force as our test charge times the electric field, right? And so if we do that, and then we divide through by Q naught, right, by our test charge, what are we going to find? Well, we know that if we divide our work by Q naught, we saw above here that we defined that, where was it, up here, that we defined this as our VAB, right? So let's go back down here. This is basically our VAB, and we know we can rewrite our VAB as VA minus VB. And then here, since we're dividing through by Q naught, if we divide out the Q naught here, well, we just end up getting this right here. And the final equal sign is just us rewriting this dot product as the cosine of the angle between the electric field and our tiny chunks of distance d, right? I'm going to remove these for the notes because I kind of write it in words, and I want to keep it nice and clean. Okay, so this is how we would go about using the electric field to find our potential difference here, our potential difference between VA and VB, right? And so if the line integral, this line integral that we see here, which I've written here, is positive, the electric field does positive work on a positive test charge as it moves from A to B. Okay, so in this case, the electric potential decreases as the test charge moves from the point A to the point B, right? So we end up with a VAB, which is going to be positive. Okay, so another way to think about this is that a positive test charge, Q naught, experiences an electric force in the direction of the electric field and toward lower values of our potential V. Okay, and the opposite would be true for a negative charge. Now I haven't left space here, but I kind of think about this sometimes in an analogy to gravity, right? So we can think of, maybe I'll draw a little something here. So we can think of, let's imagine like a mountain and then a valley and a mountain and so forth, right? And then let's imagine that we have our gravitational field or gravity acting in this direction, right? If we had an object of some positive mass m, and I mean positive mass is the only thing we have to work with, but I say positive mass now because I'm going to connect this back to positive charge afterward. But for now, let's think about just a positive mass here. Well, if this object is free to move, it wants to move in the direction of our gravity, right? It wants to move. It's experiencing a force downward because our gravity is pointing downward, right? And so it's also trying to move to lower potential energy here, right? It's trying to move into the valleys because it's trying to reduce its potential energy. It's trying to move in the direction of g. Well, this whole thing is exactly the same as the electric field. If well, the electric field and our electric potential. If this was a uniform electric field acting in the sort of downward direction here, and we replace our positive mass with simply a positive charge, then we know that our positive charge wants to move in the direction of the electric field. It's feeling a force downward here, and it's trying to move in such a way that it's minimizing its potential energy here, and that's really this v. We're trying to minimize. We're trying to move to low v here, and v simply gets lower as we go down, right? Like v is low here, and v would be higher here. Okay. And so that's kind of one way to think about this whole question of potential and electric field and how our test charge is going to move. Okay. The last thing to notice about equation 7 here is that it shows us a way that we can use, well, that we can think about our units of potential difference, right? So we know that our units of potential difference are going to be volts. But the equation also shows us that our volts, well, basically what it shows us is that if we divide out by meters, divide our volts by meters, because we end up with, basically we're ending up with volts here, and we're ending up with our newtons per coulomb times meters here, right? But if we divide out these meters, like we divide out the meters from here, we're going to end up with volts per meter is equal to newtons per coulomb, and this gives us another way to talk about the units of the electric field. Up until now, we've been referring to our electric field in terms of newtons per coulomb, but we're going to find that from now and going forward, that a more natural way to talk about the units of electric field is volts per meter. Okay, so generally speaking, when you're talking about electric field, you don't really want to use newtons per coulomb except for the first couple of weeks of the class. You're going to move on to a sort of more sophisticated definition of volts per meter. Okay, and so whenever you talk about an electric field, try to quote the magnitude of that electric field in volts per meter. Okay. Now, before I move on to some examples, because we're going to need to do a few, I'm going to talk about one more useful sort of useful thing that we can sort of pull out of this discussion here. It's this idea of electron volts. Okay, so the magnitude of the charge on the electron, which is E, right, can be used to define a useful unit of energy. Okay, and so we don't want to confuse what we're going to be doing here. Maybe I'll mention it at the end, but we're going to use this idea of the charge on an electron to define a useful unit of energy. Okay, so when a charge Q moves from a point A to a point B, where at the point A we had a potential VA, and at the point B we have a potential VB, the change in potential energy, so the change in our U is given by the expression that we see here, right? So we have the potential energy in A minus the potential energy in B. Well, that's going to be equal to Q times our VA minus VB, because we know that from this definition up here, U and V relate to each other in this way, right? So we can write that. Where was I? Down here, right? And so we can just use our shorthand to clean this up, and this is just going to be equal to Q VAB, right? Now if this Q is actually the charge of one electron given by this number here, 1.602 times 10 to the minus 19 coulombs. And if this change in potential, this potential difference is 1 volt or 1 joule per coulomb, then the change in energy is going to be given by this expression that we see here, right? We're going to end up with UA minus UB is equal to 1.602 times 10 to the minus 19 joules, right? And we define this quantity to be 1 electron volt. Okay, so 1 electron volt, as we can see it here boxed off, 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. And this is just a useful sort of unit of energy that we want to remember. Now be careful, because it has the word volts in it, you might be tempted to think that this is a measure of potential, right? Like volts are, but it's not. It's a unit of energy. Always think about it in terms of replacing joules. Okay, it's not replacing volts. It's an electron volt. It's a measure of energy. Okay. So that's the sort of theory from this section. I thought we would do a couple of examples. The book actually does 5 examples. I may insert some more into the next video from this section, or if not, I might do some of them in our in-class meetings. But for now, I'm going to go through 2 of them, and let's take a look at those. Okay, so example 23.3, we're looking at electric force and electric potential. And so let's start off. We start off with a proton. It has a charge shown here. It moves a distance d, which is a half meter, in a straight line between the points A and B. And this is in a linear accelerator. It's not that important what it's doing this in. We're given all the important information here. The electric field is uniform along this line, and it has the magnitude that we're given here. And it is in the direction of A to B, right? So they're going in the same direction. D points in the same direction as E. Okay, so we want to determine in part A the force on the proton. So let's start off by doing that. This one should be fairly simple for us, right? We know that the force is simply going to be equal to our charge times the magnitude of our electric field. I can substitute in numbers here, I guess. Actually, hold on. How much space do I have? Yeah, okay, that should be fine. Let's do it like this. Okay, so I can substitute in numbers here, and this is going to end up giving me, what is it, 1.602 times 10 to the minus 19 times our electric field, which was given to us 1.5 times 10 to the 7. And if we do that calculation, we will find that this is equal to 2.4 times 10 to the minus 12 newtons. Okay, that's simple enough. Now let's move on to part B. In part B, what are we trying to find? We want to find the work done on it by the field. Okay, so we need the work done on the charge, our proton here, by the field. So we're going to end up finding that the work in moving from A to B is going to be given by FD, right? Now why can we make this so originally we would have had to write it down like this, right? Like kind of like, do I have it anywhere here? I think I have it. Yeah. So we would have had to write it down like this, but we can simplify this dot product because we know that the force and our displacement, the direction in which this thing is going, is going to be the same, so the dot product gets eliminated. We do the integral, right? But the integral of dl from A to B just gives us d back, right? And so we end up with FD, and this f obviously would have come outside of the integral because maybe it'll be easier if I actually just write this thing out fully, right? So we're going to end up with the integral from A to B, f dot dl, but like I said, these things both point in the same direction, so this ends up being A to B f dl, but f is constant, so it can come outside of the integral, A to B dl, and doing this integral just gives us a d back, right? Because we're just integrating from A to B along a straight line, so we just get the length of that straight line back, and we end up with FD, right? And so at this point, again, we can just substitute in numbers. I have the numbers for this. What is this? 2.4 times 10 to the minus 12, and a 0.5 meters displacement here, right? And if we do that calculation, we end up with 1.2 times 10 to the minus 12 joules. Okay, that is part B. And I'm saving some space here because I have a little discussion I want to have after we do the next part. I did want to mention, actually, let me erase this. I did want to mention that we could, since we're talking about joules here and we just talked about electron volts, we could write this in terms of electron volts. So let's say we wanted this in terms of electron volts. We could simply take our 1.2 times 10 to the minus 12 and then multiply it by 1 electron volt over 1.062 times 10 to the minus 19 joules, right? To go from joules to electron volts, right? This was in joules. So if we multiply this through, we're going to end up finding that we get a work from A to B equal to 7.5 times 10 to the 6 electron volts, which we could write as 7.5 mega electron volts. Okay, so that's one way to make use of our new units here. Okay, so what are we doing in part C? And I'll start that up here. In part C, we want to look at the potential difference, VA minus VB, right? So I'm just going to write out the equation here. We have VA minus VB, which we sometimes call VAB. That's going to be equal to, well, the easiest way for us to do this now is to just use the expression that we have above here, right? We know that VAB, not this one, we'll use that one afterward, but we know that that VAB can simply be written as the work which we just calculated over the magnitude of our charge. So we can just write that out. We're just going to use work AB is equal to, well, over our charge is equal to our potential difference here, right? And so we can do that calculation. We just substitute in numbers. We just calculated what the work was. We saw it was 1.2 times 10 to the minus 12 joules. And if we put that over the charge that we're talking about here, which is 1e here, right, that value there, we end up with the value we see here. We end up with 7.5 times 10 to the 6 joules per coulomb. Okay, and this is going to be, well, I can write it like this. This is also going to be, because of what we see above here, where do we have it? Joules per coulomb. Right, joules per coulomb is 1 volt. And so if we come down here, we can also write this as 7.5 times 10 to the 6 volts, which is also 7.5 megavolts. Okay? So that's great. But what if we didn't realize, and this is not really part of the question, but we can kind of do it anyway. What if we didn't realize that we had done all this work to find the work, right? But we wanted to do it doing an integral here, right? Like, let's say we wanted to use this expression to find the work, because we know what the electric field is, we know what dl is, or we know what our d is. So can we find the potential difference that way, right? We want to use this expression to do it, expression 7. So let's do that here. How would we do that? Well, we know that VAB is just equal to VA minus VB, and this is going to be equal to the integral from A to B of E cos phi dl, right? So I'm just using the sort of dot product expanded into this version where we have the cosine between our E and our displacement d, but we know that they point in the same direction here, so this is going to go to 1, right? And so we're going to end up finding that we have the integral from A to B of E dl, but again, our electric field is constant, right? Or is uniform, I should say, and so it can be pulled outside of the integral. dl, and again we end up doing this integral, and this just gives us d, right, the distance, right? So we end up with e d, okay? And again, just by substituting in numbers, we can do that. We're going to find that our, how did I write it above here? I wrote that our VAB, so this is going to be VAB is equal to ED, but ED is actually just 1.5 times 10 to the 7, and this is 0.5 meters, right? So this was our volts per meter. This is our electric field, right, written in volts per meter, which is how the sort of new way we think about it. And this is our meters, and so our answer is going to come out in terms of volts, right? These meters are going to cancel, and the answer is going to come out in terms of volts, and it's going to be 7.5 times 10 to the 6 volts, or again the same as we found above, 7.5 megavolts. Okay, so that would be the answer to that example. I'm going to do example 23.6 next here, but I'm going to pause the video to save this again in case this thing crashes on me again. Okay, let's keep going here. So now we're going to take a look at example 23.6, and we want to find the potential by integration here. So what are we going to be doing here? We want to by integration. We want to find the electric field. Well, okay. So by integrating the electric field, we want to find our VAB using the expression that we see here, right? So we want to find the potential at a distance r from our point charge Q. Okay, and from the textbook we have this nice diagram here. We have our charge sitting at the center here at some distance a. This is where we want to find our potential. We're setting the zero potential at infinity at b, right? So we're going to end up integrating out from our r here all the way out to infinity. Okay, and so that's basically how we're gonna approach the problem. So let's begin down here. So to start off with, we've set our potential at infinity, which is our potential at b. Our b is at infinity, to be 0. Okay, so we're setting that up. Then we have this expression VA minus VB is equal to, well, now it's going to just be equal to VA, right? Because our VB goes to 0 at infinity. Okay, and so I'm just going to call this V, and this is going to be equal to the integral from R, right? This is our R pointing to our point A, so from R out to infinity of our electric field dotted into our elements dl. Now why is this? Well, this is just reusing the expression that we have right here. Yeah, so we're basically just setting b to 0, and then we're evaluating this integral here. Our a is our r, which is the vector that points to our, well, the magnitude of the vector that points to point A there, and our b is out at infinity. Okay, so let's take a look at this integral. We have the integral here. We know that we can write the electric field of a point charge as follows. So maybe I'll put that here. So we have the electric field of a point charge. Well, that's just going to be 1 over 4 pi epsilon naught. It's going to be Q, over r squared, and it's going to point in the r hat direction here. It's going to point in the direction outward, away, radially from our point charge. Okay, and our dl is just going to be equal to dr r hat. Now, why is that? Well, it's because we're basically just integrating along one line that leads from the center of our point here out to infinity, right? And it's following the same line as the electric field, which is sort of indicated by this, that both of them are r hat, right? They're both pointing in the r hat direction. Well, so this dot product is really just going to end up being r hat dot r hat, and that's just going to be 1, right? And so our integral simplifies a fair bit. We're going to end up with an integral that looks like this. V is equal to the integral from r to infinity of q over 4 pi epsilon naught r squared dr. Okay, and we should be able to do this one fairly simply. We can factor a lot of stuff out here, and so we can factor out the q and the 4 pi epsilon naught. None of those have any r dependence, and we're just looking at the integral from r to infinity of well, I'm going to write it like r to the minus 2 dr, right? And if we do that integral, we're going to find that, maybe I'll just keep it all bundled together. We're going to find that we have the following expression here. So doing this integral gives us minus r to the minus 1, right? Which I can write just as a minus 1 over r, right? And we need to evaluate this from r to infinity, right? So we can see right away that evaluating this at infinity is going to give us a 0, right? So let me do one more step down here. So this is our v, q, 4 pi epsilon naught, and then evaluating this at infinity gives us minus 1 over infinity, kind of, right? So this just ends up giving us a 0, and then we have minus 1 over r, because evaluating at r just gives us back our r. Okay, and I know it can be a little weird to sometimes think of your limit of integration as being the same variable that you're integrating over, but in this case it works out fine. We could have written down the limit as a. Instead, we could have called this a and then just changed it back to an r and let it be variable afterward. But in the end, it's just going to work out to be the same thing, so we don't have to worry about it. Let's clean this up one more step. We can see that these minus signs are going to cancel. We're just going to end up with an r in the basement, and this is going to tell us that our v is equal to q over 4 pi epsilon naught r, right? And this expression here, this is our answer. This is our potential outside of a point charge, but it's also the same as the answer we said it would be up over here, right? So it all checks out. That's exactly what we were looking for, and that's the answer to that problem. So like I said, I'm not sure exactly if I'll do more examples in the next video from this section or start off with ones from the next one, but we'll see, and I'll see you guys in the next video.